Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will derive the MGF of a very popular distribution, the binomial distribution. Okay? So, this is the problem that we want to solve. Okay? If y has a binomial distribution with parameters n and p, we want to find the MGF for y. Okay, so that's the ultimate goal. But before we tackle that problem, let me show you a result that you have seen before and that will be very useful here. Okay, let me just, let's call it useful result. Okay, so remember the binomial theorem? So let us start with a particular example. Okay, if we have a plus b squared, we know that's the same as a squared. Okay, let's change these here. A plus b, okay, a squared plus 2 times ab plus b squared. Right? And another way of expressing this would be as follows. That's a1. That's the coefficient that multiplies a, right? So that happens to be the same as 2 choose 2. That's just 1, okay? That 2 is the same as 2 choose 1. And this guy is the same as 2 choose 0. Or, let me use this notation. I like better this notation. 2 factorial divided by 2 factorial times 2 minus 2 factorial, right? Times a square plus we would have something similar here. So we would have 2 factorial, 1 factorial, and 1 factorial there, AB. And we would have something similar here. Two factorial divided by 2 minus 0 factorial times b squared, right? And now that we have those guys there, let me also change this a little bit. This is a squared times b to the power of 0. Right? That's the same as a squared. Here, just to underline the relationship that we have here, that's the same. A times b is the same as a to the power of 1, b to the power of 1, and this is the same as a to the power 0 times b squared. You guys agree? Okay. We know, right, that we could rewrite a plus b cube also in a similar way, right? This is the same as a cube plus 3 times a square b, right, plus 3 times a b square, right, plus b cube. Okay. Now, using these ideas, right, we know that this is the same as a cube times b to the power of 0, right? This would be the same as 3 times a square b to the power of 1. We have here a 1 as well as an exponent. And here we have a to the 0 power, right? Now let's talk about those coefficients that we have here, right? Let me write that down as 3, choose 3, right? This one, that 3 would be the same as 3, choose 2. This guy would be the same as 3, choose 1. And this guy here would be the same as 3, choose 0, right? And what we know is that we could also use that sigma notation, right? Let me use that sigma notation for what we have here. So let me use y as our counter, right, as our index. So in this case, y goes from 0 to 3, and we have 3, choose 3, 3, choose 2, 3, choose 1, 3, choose 0. That's the this guy is going to be the same as the exponent of a, right? So 3 choose y, a, well, times a to the power of y, b power 3 minus y. You guys agree? It's just notation for this, right? Let's see. When y equals 0, we have 3 choose 0. That would be this guy, a to the power of 0, and b 3 minus 0. That's 3. Okay, that's this guy here, the last one. When y equals 1, 3 choose 1, a to the power of 1, b squared. Make sense? So it's just notation, right? Make sense? In general, let's write that down in general. So in general, what we're going to have is that, let me copy paste this, and instead of plus b cubed, what we want in general is n. Okay, so then it would be n here, and it would be n choose y, a to the power of y, b to the power of n minus y. Okay, just another way of expressing that would be, using our formula for combinations, which is n factorial y factorial n minus y factorial. Okay? Okay. So keep in mind that guy, the binomial theorem. Okay, that's going to be useful. Okay, let's go back to our main problem. Let's try and solve that problem. So we want to find the moment generating function of y. So where would you start, right? Well, it makes sense that we are going to start by using the definition. So by definition, the moment generating function of y, and we want to underline that we are dealing with that random variable y, that this is a function of t, right? So by definition is just the expected value of e to the power ty. Okay, ty. Okay. Okay, so that's just by definition. Now remember from what we have been doing, right, regarding expected values, when we want to find the expected value of a generic function g of y, what we do is, in this case, in the discrete random variable case, it would be the sum of g of y times, right, the probability mass function, right? So we have the sum for all possible values of y. In this case, y goes from 0 up to n, right? Y, remember, represents the number of successes in a series of n trials. So we could have 0 successes, 1, 2, up to n, and anything in between. And as we said, the expected value of g of y would be the sum of g of y. In this case, g of y would be this guy, right? It's a function of y. Times the probability that the random variable assumes that particular value y. Okay, so the probability mass function, and the probability mass function for binomial random variable, right, we know is going to be n choose y. Let me write it down here. N choose y, it's the same as n factorial divided by y factorial times n minus y factorial times p to the power of y times 1 minus p to the power n minus y. Okay? Okay. So, now let's try and do a little bit of algebra and see if we could simplify this expression. So let me copy paste this guy. I just want to make it look nicer. So first, note that e to the power ty is the same as e to the power of t to the y, right? So we could rewrite this, right? We have p to the y times e to the ty, right? So we could rewrite that like this: e to the power of let me do it like this: e to the power of t, right? But this to the power y. Makes sense? It's the same, right? This would be p to the power of y, e to the t to the power of y. It's just going to be ty, right? So we're not doing anything illegal. Makes sense, right? Okay. Now, let A be this guy. And B be this guy. Okay, we're going to make a change of variables, if you will. Let's relabel what we have there. Then what we have here is A and B, right? But remember that result that we mentioned at the beginning? Sum of y going from 0 up to n of n choose y a to the y times b to the n minus y power. Right? So that happens to be just a plus b to the power of n by the binomial theorem, right? Let me say that. So by the binomial theorem, this is just a plus b to the power n, right? But now let's go back to what we had before, right? Which is equivalent to, in our case, right, what we had for A and B was this: B times e to the t, right? And B was 1 minus p, right? A was e, let me write it like this, p e to the power of t plus 1 minus p, the whole thing to the n power, right? And that is the MGF of our random variable y. How's that? Nice, right? So the key here was doing a little bit of algebra and using the binomial theorem. Okay? Now, remember that one of the applications of MGFs, is suggested by its name. It's going to help you to find the moments with respect to the origin of random variable, right? So what we said is that, for instance, the first moment with respect to the origin is going to be the expected value, right? And what we said is that if you have the MGF of a random variable, if you want to find its expected value, a possible approach is taking the derivative with respect to t of your MGF, and once you have it, you evaluate it at 0, at t equals to 0, right? And there you are. You should have your expected value. Okay, so just for fun, how about we test drive our MGF and see if it works? We know that the expected value for a binomial random variable is MP, right? Okay, so just for fun, let's find the expected value of y using the MGF. So first step, as we said, we need the derivative with respect to t. Really important. Okay, so let me stress that out here, because it's the derivative with respect to t. Okay, of this guy. Okay, so that would be the same as n times p times e to the power of t plus 1 minus p times, right, by the chain rule, well, it would be n times pet plus 1 minus p to the power n minus 1 times the derivative of this guy, right, with respect to t by the chain rule. Okay, so let me copy paste this. So we have n here, we have n minus 1 here, and by the chain rule we need the derivative of this inside the square brackets, but this is a constant with respect to t, so we don't worry about that guy. And then the derivative of p times e to the power of t, well, it happens to be p e t, right? Okay. You guys agree? Okay, let's keep going. So let me rewrite this just like this. This is going to be n times p e to the power of t times this p e t plus 1 minus p to the power n minus 1, right? And this, let me just use a different notation here. I just wanted to stress, to underline that we were taking the derivative with respect to t. Okay, let me use this notation here. Okay, and this should be a capital Y to be more consistent with the notation. Okay, so now we know that to find the expected value, what we need is to evaluate that derivative at 0, right? Okay, so let's do that. Let's evaluate at 0. And that happens to be n times p e to the power of 0, right? Let's write it down just to be, you know, extra careful. Okay, there we are. Just to be explicit, right, we are doing this, but e to the power of 0 is just 1. E to the power of 0, that's just 1. And then we are going to have p plus 1 minus p. Then we have 1 to the power n minus 1. So that's just a 1. And then we have p times n, or n times p, right? And we know that is the right answer. So it seems that we found the right expression. Okay? Okay, so just to summarize, what we did here in this video was finding the MGF of a binomial random variable. It's given by that expression, okay? And then at the end, just to check our work, we decided to use that MGF, that expression we found, to compute the expected value of a binomial random variable. And we ended up with, you know, what we should, n times p. Okay, so that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.